So we have curve and we have vector field. So f equals to pq. So we're talking about two-dimensional. And here we assume it's continuous. It has continuous first-order derivatives. D. So we have a region D, and function f is continuous and has continuous first-order derivatives. And we have C, which is curve, is closed, simple, counterclockwise, positive direction. So counterclockwise. Piecewise continuous. So we have that two pieces. Then we would take integral, line integral over C, function f dot dr. And you're going to be using, because it's closed, I kind of want to emphasize and put that closed thing on the integral sign as well, kind of fancy notation, which is, again, I'm going to put that closed here, just to emphasize it's closed. And that is, if you recall, that is just pdx plus qdy. And that is going to be now equals to double integral over d derivative of q with respect to x minus derivative of p with respect to y dA. It's double integral now. And here C is boundary of D. Okay. So that's what the Green's theorem is. Okay, now maybe need to explain a little bit more about what closed and simple means. And I will draw a picture, and then maybe hopefully it will be clear what I'm talking about. So that is simple. That's not simple. This one is not simple because it intersects with itself. Okay, so let's drop. Okay, so simple means no intersecting, the curve does not intersect with itself. Okay, and closed means closed. Closed means you started and you finish where it's closed. That's also closed. The one on the left is closed and simple. And this one is closed, but not simple. And so we want to be working for Green's theorem with curves which are simple and closed, look like this. Then the region D will be inside. Curve C will be the boundary, and we want to move counterclockwise along that curve. Okay, so that's what the theorem is saying. Okay, let me write down an example. F equals 2y plus square root of 9 plus x squared, 5x plus e raised to arctangent y. Calculate work done. Along positive, which is counterclockwise oriented, x squared plus y squared equals to 4. So we calculate and the following integral over c. C is going to be this guy. So it's closed. FDR. So we're going to get C. So C is going to be x squared plus y squared equals to 4. So it looks like this. And we're moving along that in a positive direction. It's closed, right? So two y plus square root of 9 plus x squared dx plus 5x plus e to arctan y dy. So that's what we got. Now we're going to apply the green theorem. Green's theorem. We definitely don't want to do this integral directly because I look at it, I immediately scared of that e raised to arctangent y, and it's going to be, I don't want to go there. So I apply greens. And if I apply greens, then that is p, that is q. Green's theorem tells me switch to double integral. Region D. D is going to be inside boundary by the curve. Take derivative of q with respect to x. So because it's we already have y, so we're taken with respect to x. Take derivative of p with respect to y, because it already has x. Subtract. So what you notice is if you subtract and it equals to 0, your double integral will give you 0. And that's going to be 0 because we're going to be doing work over conservative field, right? That's exactly what we did the last time. So if our difference equals to 0, it means we're working over conservative field, and work done over conservative field is going to be 0. So anyhow, dA. So we're going to get double integral over d. So d with respect to x is going to be 5 of q minus d with p with respect to y is going to be 2 dA. So you're going to get 3 dA. And you remember double integral of 1 is going to give you area, and we're talking about unit, not unit circle, but circle of with radius 2. So its area is going to be 4 times pi r squared, so 4 pi, and we multiply by x sub 3, so we're going to get 12 pi. Okay. Because that is area. If you like, switch to polar or whatever coordinates, you will be able to calculate it. So let me now maybe outline why the Green's theorem is working. So again, Green's theorem was saying the following. So we have line integral over C over close C p dx plus q dy equals double integral r partial derivative respect to x minus partial derivative respect to y dA, right? So in a sense, it's telling us two things. So it's basically telling us the two things. P dx equals to double integral r negative partial derivative respect to y dA. And the second one saying that partial derivative q dy is equal to double integral, it's probably r d better, used d before. Partial derivative of q with respect to x, double integral of it with respect to y. So that's basically what it's saying. You can break it in two pieces, so that's essentially what we're doing. So I will concentrate on that piece. Okay. So we'll concentrate on that piece, and I'll try to explain why that piece is working. Okay. So let's try. Again, I will oversimplify the situation. I will oversimplify the situation, and I will assume what we have x and y axis. Then we have our boundary looks maybe like this. Okay, so type 1. So our boundary is going to be consistent or going counterclockwise. It's going to consist of 4 pieces, C1, C2, C3, and C4. So C4 will be basically telling us that, let's put A here, that x equals to A. C2 will be basically telling us that x equals to B. And C1 will be x changing from A to B. And Y will be, let's put like function here, Y equals G1 of X. C3 will be X is changing because we're going from B to A, so B on the bottom, A on top. And for C3, I'm going to be writing down function Y equals, say, G2 of X. Okay. And I'm concentrated. I said I will be doing this piece. Okay. So we calculated integral p dx over that path. So let me concentrate to calculate the integral p dx. So if I will be calculating integral p dx, it's going to be integral over c1 p dx plus integral c2 p dx plus integral c3 p dx plus integral c4 p dx. C2 and C4, if you look at them, then for both of them, dx equals to 0 because x is not changing. So C2 and C4 will just disappear. Okay. For C1, we're going to use this information. For C2, we're going to be using that information. for C3, we're going to be using that. So if we do that, for C1, we're going to get integral from A to B, P x of G1 of x dx plus, for C3, we're going to get integral from B to A, B to A P x G2 of x dx. If you notice, then when we are here, when integral is going in the wrong way, instead of going left to right, we're going to left to right. So that is going to be equal to negation integral from A to B, P of x, G2 of x dx. Okay. So we're going to integral from A to B. So now I can glue them together. I can glue these two pieces together, that piece and this piece, and minus in between. So dx on the outside. So P minus P x G2x. Okay, so let me move on to the next page. Write it one more time, what we've got. And you notice is what we have inside is kind of, you'd pretend that is your antiderivative with respect to y. So we take its partial derivative. If we pretend that's your antiderivative with respect to y, then you start with partial derivative with respect to y. And on top, we're going to have G1. On the bottom, we are going to have G2. And that is essentially our double integral over D. The only thing is we mixed up the signs, top and bottom. So our function on top is actually the one which is on the bottom, and one on top is the one which is on the bottom, if you recall our picture. So G1 should be on the bottom, G2 should be on the top. We switch them. Because we switch them, the price to pay is minus, and that's why we have minus here. Okay, so that's kind of outline why it works. I showed it for type 1 region, but more general, it's more confusing. Okay, so that's how Green's theorem is working, and that's why it does work. So I'll say we have triangle, and that's our path curve. So C is closed curve. So 0, 0 here, 1, 0 here, 0, 1. Okay. So let's see. So C consists of 3 pieces, C1, C2, C3. Our function vector field is x squared plus y squared and negative 2xy. So find line integral of FDR. So because path is closed, simple, no intersecting with itself. So what we'll do is we're going to apply green. So we're going to go double integral over region D, P and Q. So we're going to take derivative of q with respect to x. We're going to get negative 2y. Derivative of p with respect to y, we're going to get 2y. Okay. Substituting it. Partial derivative of q with respect to x minus partial derivative of p with respect to y. So we're going to get negative 2y minus 2y d. Negative 4y dA over d. And now that simple integral now, type 1 region, so type 1, d is type 1. I will treat it as type 1, that's my default type 1. So, and y is encircled between 0 on the bottom, and on top it's going to be the line, so y will be from here to here. Line is, slope is negative 1, y-intercept is 1, so y equals negative x plus 1. So we're going to get integral 0 to 1, integral 0 to negative x plus 1, negative 4y dy dx. So that's what I did if I did type 1 region. 1, 0 to negative x plus 1, negative 4y dy dx, 0 to 1, negative 2y squared, 0 to negative x plus 1 dx, 0 to 1, negative 2, negative x plus 1 squared dx. If needed, do substitution u equals negative x plus 1. So we should be able to get 2 over 3 negative x plus 1 cube. And then we do it from 0 to 1. So substituting 1, we're going to get 0. Substituting 0, we're going to get 2/3, so negative. Something like that.